Thank you very much, Rainer. I'd like to thank the organizers for the wonderful invitation, and I want to indeed add to what Rainer says. It's wonderful to see so many friends and colleagues after such a long time. So the title of this talk is the extrapolation of correlation, but it's really the extrapolation of covariance. I just couldn't resist the rhyme. And I tried to think about whether it ties in with the theme of the workshop, which is about prediction and forecasting. And to some extent it does, because you could really think about it as how do you forecast unseen correlations or covariances. And I'll try to make that precise, of course, very quickly. I should say this is joint work with my PhD student, Kardik Wagmer, and you can read more on the archive in the corresponding paper. So I'm just going to jump straight into the problem statement. Okay? So here's the problem. Suppose that I give you the interval 0, 1, and I give you a cover of 0, 1. So a collection of intervals. They may very well be overlapping, but as a whole they cover 0, 1. I then form the rectangles corresponding to each of the elements of this cover, and I take their union. So if you have a finite number of intervals, what you're going to get is you're going to get this arrangement of squares strewn across the diagonal symmetrically with respect to the diagonal that kind of cover the entire diagonal. If there are uncountably many, you can get sort of more fancy regions, but the intuitive notion is that this domain omega that you get is some neighborhood around the diagonal, and in particular we will call such a domain serrated when you have finitely many elements in the cover. Serrated because of the zigzag. It looks like a serration. This sort of domain will be called the nearly serrated domain, and I would tell you about nearly serrated domains, after 40 minutes, but I don't know that I will have time to tell you about them within the time limitation. So now let's define a partial covariance function on this domain. What does it mean to have a partial covariance function? A covariance has to be defined over a square domain if it's going to be positive definite. So the idea is that if you restrict on any subsquare that is symmetric along the diagonal, it will be positive definite on that subsquare. And this is this little footnote. So the problem is, if I define a partial covariance on this subdomain omega, how can you extend it to a covariance on the complete domain 0, 1 squared? Not at all, not at all. What I really mean is, intuitively what you want to think is that k omega is a covariance. So take a covariance on 0, 1 squared and then restrict it on this domain. This is a valid partial covariance. However, I'm considering situations where this k omega might not a priori be defined by the restriction of a global covariance, in the sense that I'm not a priori assuming that a global covariance even exists. And this leads me to a refined list of questions that you can ask. Does there even exist a completion? If so, how many completions? What are conditions for completions to be unique? Are there completions that can be constructively manifested? Are there completions that are natural or canonical? You might ask, what do we need to impose as a condition for uniqueness? What happens to a completion if we perturb the data a little bit? So if I perturb k omega, does the completion depend continuously on the input? And of course, it's natural for us to ask, how do all these questions relate to the underlying Gaussian process with a partial covariance k omega, in the sense that if you restrict, if you take x at u and x at v, where u and v belong in omega, then the covariance of x at u with x at v will be given by this k omega partial covariance at u and v. So, as most of you are thinking, surely this problem has been solved in 1926, and it has been in special cases. Okay, this is a very classical problem. You can imagine that because positive definite functions are ubiquitous in math, there are connections with probability, with analysis, and possibly beyond. But what special cases have been considered? So for example, in analysis and probability, a classical question is the continuation of a positive definite function. So a positive definite function is a special case of the problem that I just described, when the partial covariance is actually given by a function of the difference of the two arguments. Otherwise said, if you restrict to a stationary partial covariance, you recover the question of completion of positive definite functions. And of course, the domain now would be a band. Okay, so the question would be, given a positive definite function on an interval symmetric around 0, can be uniquely extended? This has connections with probability. Questions that were asked at the beginning of the previous century related to, for example, would knowing the characteristic function at an origin of 0 determine a distribution? And there are major results there. They go back to Kara-Theodori with the trigonometric moment problem, Gnedenko-Assine, Krein and co-workers, it's fair to say, I think, comprehensively settled this stationary one-dimensional case, and then further work in the stationary and/or isotropic case by Calderon, Rudin, closer to our neck of the woods, Tillman Gneiding. What about statistics? Well, I mentioned Tillman Gneiding, although I think these are math papers that I mentioned. In statistics as well, this has been considered, this is a special case of problems being considered related to matrix completion, covariance matrix completion. It's a special pattern that I described here, of course, because I'm thinking of processes. But problems of this nature have been considered by Israel Goldberg and co-authors, Johnson and Dempster. And how did I come to this problem? I came to this problem through functional data analysis, where we don't necessarily want to restrict attention to a stationary process and a stationary covariance. And we ask the following question. Imagine that there is a process X. So a priori, there's a covariance on 0, 1 squared that corresponds to a process X. And I am able to observe many realizations of X, but censored, in the sense that I can only observe them on some subintervals of 0, 1. What can I say in terms of inference about the whole covariance? So this is a sketch of what I mean. Normally I would be able to observe replications, let's say independent replications of the process X. And if I have these 5 independent replications, I subtract the mean, I take tensor products, then I have information on covariance of the complete square. Because if you ask me, what information do you have about the covariance at 0.2 and 0.8, I have 5 measurements on this covariance. Okay, so I have kind of rank 5 information everywhere on the square. But I'm thinking of a situation where I only get to see a fragment, a short subinterval of each process at different locations. And so if you look at what happens here, if you do the same thing, subtract a mean, you can estimate a mean by pooling everything. But then look at covariance information, you can see that you have covariance information only on a serrated domain. In some regions, you have more information because you get to observe more pairs. In other regions, for example, here and here, we only have rank 1 information. And this arises very concretely. This is a data set considered, I think, by Roch Delaigle and Peter Hall. It's measurements on bone mineral density on 117 young women and girls. So to measure this, you have to go into you have to do X-rays. Okay, so it's not an easy measurement to do. So notice that each subject is measured a few times in some short interval, but the duration of the study, so the time scale at which we're interested in the phenomenon, is much longer than the time we follow each individual. So each latent process is measured during a short time interval. There's more complications, right? The measurements are discrete. There's possibly measurement error. I will get to this eventually. But if you look at the kind of covariance information that you have, you see roughly the pattern on the right. Okay, so I'm plotting points, pairs of points on which we have covariance information, and you see that a serrated domain roughly is being sketched. And you would like to know the complete covariance because that's the starting point to, for example, predict the missing part of individual curves, input the curves as the covariates of a regression, do testing, classification, and so on and so forth. All right, so there has been previous work on this in the functional data analysis community, including some of my own, but the focus had been very firmly on determining conditions for identifiability. And somehow identifiability was almost subconsciously seen as being equivalent to uniqueness. So what are the conditions that we need to impose to ensure uniqueness of completion? What I would like to do here, and what the focus of our work was to go in a different direction, to say, let's look at the set of all possible completions, so all covariances on 0, 1 squared, such that when restricted on omega, you get the partial covariance k omega. And let's try to really understand this set. As part of this effort, we might understand uniqueness, but maybe we can say more. You can see immediately that this is a convex set. It's bounded if the covariance k omega is bounded along the diagonal. So you can quite quickly start to surmise that it's the kind of set that's either empty, has a unique element, or has uncountably many elements. So let's try to understand this, and let's go to the simplest non-trivial case, the two serrated case. So I only have two intervals, 0 to b and a to 1, with a less than or equal to b, so it's a kind of overlap like this, and you get two overlapping squares. They might overlap at a point, but they certainly do overlap because you need to have a cover, and this gives you the domain omega. And I'm going to cheat. I'm going to give you the answer and tell you, here is a completion, or here is a suggested completion, and then try to explain why it makes sense to consider a formula like this. So here's the formula. Of course, the completion is going to be equal to the partial covariance as given within the domain omega. And then if you give me a point, st, outside of that domain, here's what I'm going to do. I'm going to first ask you to think about this as a matrix. And I know it's a little complicated because with a matrix, the diagonal would be going in the other direction. But think about the matrix that is formed by the intersection of the two squares. And think about a column vector that looks at this section. Literally, you have a function on 2 dimensions. Consider its restriction on this section. Think about it as a column vector. Consider the other restriction on this section. These sections are highlighted by the intersection, okay? And then take the inner product that is this vector times the inverse of this matrix times this column vector. And this is what I've written down here, except of course to make sense of what I just described in the case of a covariance function, I phrase this in terms of a reproducing kernel Hilbert space inner product. So the inner product of this section with this section under the RKHS inner product generated by the intersection of the two squares. In particular, the statement I'm making contains within it an assumption, and rather an assertion, that this inner product makes sense. So that this section and this section are in this RKHS, and that this inverse sort of applied to these vectors makes sense. Very well, so what can we say about this? If you define this extension, it is a bona fide covariance. And since it is a covariance, and clearly its restriction agrees with k omega, it is a valid completion. It needs to be a partial covariance. So
if it's guaranteed,
this completion will always exist. Exactly. So the set of completions is never empty.
I'm only saying that.
It's not easy to have a partial covariance, right? On every restriction on a subsquare along the diagonal, you need to have a positive definite function. So it's easy to dream it up if you restrict an existing covariance. Okay, that was a two-serrated domain, but I hope you will agree with me that once we've done the two-serrated domain, we've done an arbitrary m-serrated domain. And here's the idea. If you have m squares now, let's just focus on the first two and just consider this big square as a problem in itself. we know how to carry out an extension and fill this part and this part. And by doing this, with the formula I showed you, we end up with an m-1 serrated domain. And you can keep going until you exhaust everything. The outcome will be a valid completion. In fact, you might argue, why did you start from the start but not the end or the middle? Fact of the matter is that if you recursively apply the two serrated completion formula, you will arrive at the same and valid completion. You might ask now, okay, this is a way to construct a completion. How did you arrive at this? I described it in the case of matrices and vectors because this is the kind of formula you would see if you were to impose, for example, some low-rank conditions and then have some conditions that allow the invertibility of some matrices. This is the kind of formula you would arrive at. It's also the kind of formula that you would arrive at in the matrix case if you were trying to find a determinant maximizing completion, a maximum entropy completion in the Gaussian case. So, of course, that's where we decided we would start. But here, of course, you don't have things like some kinds of matrix factorizations that are used, or even the notion of determinant, at least in its traditional sense. So you need to really use RKHS technology. Okay, that's a valid completion. Does it make any sense? Now, I don't have the time to work out an example in detail, but you could do the following experiment. You could say, let's take Brownian motion. Let's take minimum of S and T on the square. Let's just restrict it to an M serrated domain. We know a completion exists. It's the completion of Brownian motion. We can apply this formula because we know what the RKHS associated with a restriction of Brownian motion in a subinterval is. We know through Sobolev spaces. If you do it, you get Brownian motion. So, if you take a few test cases, you get the right answer. So you might actually ask, is there anything canonical about this method of completion? I would have to really go into definitions and I don't have the time, but it is canonical, and the very first statement is really a theorem. It's non-trivial. Among all possible completions, this completion K star will be the unique one to possess the global Markov property with respect to the edge set given by omega. And I don't have time to, those of you from spatial statistics know what I'm talking about. Maybe if you're in high dimensional statistics, I would say that K star is the only extension such that the Gaussian process with that covariance has a graphical model structure with respect to the graph induced by omega. So you think about the vertex set 0, 1, the edge set omega. Intuitively, omega contains all of the sort of covariance information. If omega were a short band, then the global Markov property would be saying that you basically have a Markov process with a short memory. Okay? And so the canonical completion, and you can make this very precise, but intuitively, it relies exclusively on the correlations that you have seen, and it propagates those correlations to a completion by way of a Markov structure. What kind of Markov structure? The maximal possible Markov structure you can fit into omega. And it is unique in doing so among all completions. And that's why we call this completion the canonical completion. And it has been called the canonical completion before. Then, that would have been a spoiler. But it's canonical in this infinite dimensional setting as well. In particular, it shows you that if you're interested in identifiability, you might not necessarily look for uniqueness. You might a priori impose a Markov type assumption, and this will give you identifiability, because if you have a Markov assumption, then you know that there is only one completion compatible with your partial covariance, and that will be the canonical completion. But if you do want to talk about uniqueness, you can, and in fact we were able to obtain necessary and sufficient conditions for the set of completions to contain a single element, so for a unique completion to be compatible with a partial covariance. And the list looks long, but in fact, what the statement says is that if you have an M-serrated domain, then making the statement that a unique completion alone is admissible is equivalent to saying the following thing. Let's just think about the covariance at each of these subsquares as the covariance of a Gaussian process. And so the jth subsquare corresponds to the Gaussian process xj. That's just the restriction of a process on the interval ij. So under uniqueness holds if and only if one of these restrictions generates all the rest by deterministic linear transformation. So in particular, it means that all of the stochasticity of the process is contained on one of these subintervals and is propagated to the rest by linear transformation. Contrary to this stochastic Markovian propagation that the canonical completion corresponds to, the unique completion corresponds to linear deterministic propagation. Okay? And the last statement here is how you can check that condition. You can actually construct Schur complements of covariance kernels, just like you would do with matrices, and you can check if these vanish. So there's a number of qualitative conclusions to be drawn from this. One, which I've highlighted in red, is that an appealing feature is that this condition is checkable at the level of the observable. So k omega is an observable. You can actually construct all these Schur complements. It's a linear number with respect to the number of squares that you have. If one of them fails to vanish, or if you've actually not one of them, because you need to check with many starting points, but if you can look, if at some point something doesn't vanish, then you don't have uniqueness. And that's useful because some of the uniqueness conditions imposed before were not checkable at the level of observable. So you might, for example, assume that you have a finite rank overall, or that you have an analytic covariance, and then you get analytic continuation. The other thing it shows is that uniqueness is extremely rigid in assumption. It basically degenerates the process. And as I said, if you really want to have an estimable target, you don't need uniqueness. What you need, one way that you can look at it is that you need canonicity. In other words, this omega Markov assumption. So let me just give you just a plot. And I think this is useful because a referee asked an interesting question. They said, okay, you have this result. Previous authors have put rank conditions and analyticity conditions. What is the gap? And the gap is very substantial. If you think about analyticity, that's also kind of a condition that gives deterministic propagation. If you have a stochastic process with analytic sample path, let's say, then, just if you look at an infinitesimally small open interval, you look at the process on this interval, it defines everything everywhere. If you have a rank constraint, then again, just because things are constrained by the rank assumption, you can determine everything. But in fact, it doesn't have to do with rank, and it doesn't have to do with smoothness. It has to do with a rigidity of the propagation of correlation, this deterministic propagation. So here is something that is definitely not smooth and is not finite rank, but it trivializes in the sense of uniqueness. What I've done is I've taken two intervals. This is a two serrated example. One is from 0 to 2/3. The other is from 1/3 to 1. And what I've done is I've generated a Brownian motion at their intersection. So you have independent Brownian motions here, certainly infinite dimensional, certainly not smooth. And then what I've done is I've just reflected this Brownian motion to the left like this, and then to the right like that. This reflection is such a deterministic linear transformation. The process has a covariance that admits a unique completion, but of course it's very far from analytic or finite rank. So that says something about the canonical completion. What can we say about the set of completions as a whole? It turns out that the canonical completion is also elemental in describing this set, in that you can construct any other valid completion by pivoting on the canonical completion. In particular, you can prove in the two serrated case, of course, this is a simple statement, we'll go to the m serrated case very soon, that K is a completion of K omega if and only if it can be written as the canonical completion K star plus a valid cross-covariance operator. Okay? Which cross-covariance operators are valid? Any cross-covariance operator that can be assigned to a process x1 and a process x2 that marginally have as covariance operators the restriction of K omega to this subsquare and that subsquare respectively. What are those subsquare? You just take the intersection of the two squares forming the two serrated domain and you look at the squares that are formed if you move away from that intersection. So as C ranges over all possible such cross covariances, then you construct all possible completions. And the statement I would like to make is that, valid such C are very easily obtained. I'm going pretty fast, but if you think about it intuitively, all I've said in the previous slide, if you think about it in a 3x3 covariance matrix case, is that I'm giving you one variance and another variance, and I'm asking you what are the valid covariances that you can put off the diagonal. The answer is, it's just a question of picking a correlation, standard deviations, and that's what you get to do. In operator notation, you could say that the covariance operator associated with any completion will be that associated with a canonical completion. And then when you want to define it by acting on a function, what you would do is that you would branch this function. You would consider its restriction on I1 minus I2, the intersection, and I2 minus I1. And then you would also apply this cross-covariance operator. To define it, you need to define two of this sort of block matrix entries. These are the cross-covariances compatible with the two covariances that I showed you. And again, we know how to construct them. We need to pick a correlation operator. This L1 1/2 and L2 1/2 are simply the square roots of this operator and that operator. And I just wrote it that way because it wouldn't fit in one line otherwise. Okay? So, if you want to construct any completion, pick the canonical completion, pick your favorite correlation structure, and you can get another completion. But this shows to us that other completions, other than the canonical completion, though they are easily obtained, they are arbitrarily obtained because your choice of this psi, so this psi is just going to be a bounded operator with norm less than or equal to 1. It's a correlation operator. You can choose it in any way you want. But these are correlations that you are now introducing and that you never observed in the partial covariance structure. This horrible slide describes what happens in the M-serrated case. And just to unpack it, I'm just going to say you don't really need to understand everything that's going on. In the M-serrated case, we need to express an arbitrary completion by looking at its action on a function, but now we need to somehow write this function in terms of I1 minus I2, the intersection, I2 minus I3. You have to, it's a much more complicated formula. The canonical completion itself is constructed iteratively. But the point here is that everything you see in black in this formula comes from the partial covariance itself. Okay? In particular, this RP, you have an RP here. It's a joint. The IPs are just restrictions on intersections. The RP is basically what you get on the pth step of the completion algorithm. And then notice UP and VP are also defined via the pth step of the completion algorithm. The only thing that is arbitrary is, a collection of M correlation operators psi p. So again, if you think about it, try to think about it intuitively, it's a two serrated image, but a little bit more complicated. At each step, you pick a correlation to assign. And just to show you what these RPs and JPs and so on are, at the pth step of the algorithm, you have completed everything in this square here, and you are trying to figure out this region RP in this sort of inner product, RKHS inner product I showed you, in the sense of operators can be seen as basically taking somehow this operator times the inverse of this one times the inverse of this one and getting this bit here, just to show you a bit the correspondence. All right, so let's just move to estimation. If you're an analyst, you can think about this as stability. So what happens to the canonical completion if I perturb it a little bit? I mean, we're motivated by a statistical problem. We would like to say, what happens if we don't actually observe the true k omega, but we can only access an estimator? And the kind of result I'm going to try and give you is a result that somehow is a plug-in estimator. So give me your favorite estimator of the partial covariance on the basis of the data. I'm going to try and express the quality of estimation of the canonical completion as a function of the quality of estimation of k omega by your favorite estimator. And this is important because you might be in contexts where the stochastic process is perfectly observed. It might be observed on a dense grid with no measurement error. It might be sparsely observed with measurement error. And the idea is, if you have a theory for estimating covariance under an estimation regime, plug it in here and see what happens. How are we going to, why does it make sense to estimate the canonical completion? I would argue that it's always an identifiable and interpretable target of estimation, even if you don't have uniqueness. And if you do have uniqueness, if you're fortunate, you will get the unique completion by the canonical completion formula. So, kind of adapt to uniqueness. I say adapt in a very loose sense here. Okay? But there is a price to pay. In previous work that imposed uniqueness a priori via an assumption, no criticism, I've done that too. You know that a unique completion exists a priori. So you know that you can safely extrapolate, which means that you can use, somehow a series estimator for k omega, and a series estimator, of course, can be extended and extrapolated quite easily. So you can get some very nice theory and very nice rates if a priori you are guaranteed to have uniqueness. In our case, because we need to assure that our estimator will be a valid canonical completion, we need to satisfy this nasty system of equations. Okay? It's empirical version. And if you notice, there's a -1/2 here, and that's a compact operator. In fact, it's a trace class operator. So actually, it's an inverse problem that you need to solve. And the way we're going to do it is that we are going to plug in the empirical versions of all the objects of that formula you get through your favorite estimator, with the only difference that when we get to the empirical version of this RP, R hat P, we're going to use spectral truncation on the M operators that are inverted here. And so we're going to have M regularization parameters indexed by P, which are the dimension at which we truncate. Initially, we were doing Tikhonov regularization. We switched to this because here, at least, you have some intuition about how you can pick this NP. Each RP, you look at it as an operator. You can use your favorite PCA rule, for example, and you can pick a value. So what happens if you do this? Well, assuming that the spectral decay of the covariance, the partial covariance restricted on the subsquares, is a sort of power decay, a standard assumption in functional inverse problems, and indeed that this RP can be approximated in some power type level of approximation regulated by an exponent beta. Here you have an exponent alpha. Then what you get, and I've simplified this theorem a little bit, it's a little bit more technical to state, is that you can translate your rate of convergence in the L2 norm, or the Hilbert-Schmidt norm if you look at the operators, to a rate for your estimator of the canonical completion. I'm sorry, I'm missing. Yes, it's the other way around. So if you want to get a rate on the canonical completion estimator, you look at the rate of your estimator for the partial covariance, but it's raised to an exponent. Okay, so it's not 1. This exponent has this usual fractional form that you get in inverse problems. It depends on the alpha and on the beta, and of course you need to tune your tuning parameters accordingly. So in theory, you have theory that tells you what this rate is. You know this rate for a wide class of estimators, and you need to tune your parameters accordingly. Quick observations. The main issue here is that higher smoothness worsens that decay rate, which is counterintuitive. You would expect that a smoother covariance is easier to estimate, but again, you go through an inverse problem. But of course, if the things you're trying to approximate by finite dimensional projections are effectively low dimensional, then this improves your convergence rate. the most pessimistic message is that your convergence rate worsens with m. The finer the serration, the worse the rate seems to get. We think that it's not quite so pessimistic in practice, and I should stop here. I just wanted to show you 3 pictures just to show you that you can actually do this. So this is the bone mineral density example, and this is the extension that we get. In yellow kind of is the partial covariance estimated via smoothing, and then the rest is the extension. And then we have some simulated examples. We tried things like, analytic covariances, covariance of Brownian motion, finite Rankine analytic, infinite Rankine analytic. Most interestingly, and I'm not going to go into detail in this plot, what we saw is that growing the serration did not actually result in considerable damage to the estimator, contrary to the pessimistic message of the theorem. But it does tell you that in practice, when of course you don't get perfect squares, you get more of a picture like this, you need to make a decision on how many elements you're going to use in your serration. And in practice, what we would recommend is, try and get as few elements as possible. And you also need to take into account that you want these elements to be well occupied by points. You want them to be well estimable. So I will conclude here, and thank you very much.